All right. So I'm going to talk about Module 5, some of the key points. Um, for more in depth, you definitely should watch the full lectures. Um, but a lot of what I give in those lectures is background. Um, and you don't necessarily really need to understand the quantum mechanics all that much. What you really need is a surface understanding, and you got to take away some key features about um, orbitals and hybridization that we're going to carry forward. Uh, all right, so the key points about orbitals. Um, Orbitals are all based on mathematical functions. Okay, you don't really need to understand exactly how they're based on mathematical functions. You just need to know that anytime we draw a picture of an orbital, it comes from some really complicated math that someone else has done for us, and that you, if you really want to do someday, after taking lots more math and some physics, then you can maybe do it. Um, I could do it at one point in my life. I cannot at this point in my life. Um, so this is one where if you just accept some of the results, if you accept that we have these things called orbitals, or at least that this model works, if you accept that we have this model that works, then that's good. You don't really need to worry too much about understanding it from top to bottom. So we have these things called orbitals. We can combine them to make new ones, just like you can combine two functions. So in a math class, you might be given f of x and g of x, and said, "Oh, what is f plus g of f of x plus g of x?" Have you ever done that in a math class? Yes. Does that sound familiar? Yeah. So you can add two functions together. We can add two orbitals together. When we add two orbitals, the thing is, the function can be either positive or negative. And when you add two functions together, if they're both positive, you get a bigger number. If they're both negative, you get a bigger number. It's a bigger negative number, but it's a bigger number. But when you add two things with opposite signs, a positive and a negative, you end up with a smaller value because they cancel each other out. So when you combine orbitals, they get bigger wherever the functions have the same sign. They get smaller wherever the functions have opposite sign. Those are the key things to keep in mind. And, for a couple of detailed examples, you can look at the AP Chem lectures. I don't want to rehash them right now. But I do a couple of specific examples there of showing what this looks like pictorially. Any questions about what I just said? Okay. So as far as hybridization, we start out with these atomic orbitals called s orbitals and p orbitals. In this class, we'll never deal with d orbitals or f orbitals. So if you've learned about d or f orbitals in the past, great, but you don't need that knowledge at all. All right. But we start out with each atom in its valence shell has each atom has three orbitals in its valence shell. The s orbital and the three p orbitals. We call them px, py, and pz because they point along the x-axis, the y-axis, and the z-axis in 3 dimensions. Okay. But the thing is, we have atoms with different shapes. We have atoms that are linear. We have atoms that are trigonal planar. We have atoms that are tetrahedral. And the s and the p orbitals don't really match those shapes. So what we do is we use essentially kind of a mathematical blender that says, okay, take a little bit of the s orbital and a little bit of this p orbital and a little bit of that p orbital and put them together and make a new combination. Okay? And so we come up with these 3 different combinations that we can make. All right? When an atom is linear, we call it sp hybridization. And we say it would have 2 sp hybrid orbitals. All right? One of them would point in one direction, and the other one would point in the other direction. So this is one sp orbital, and then the red one represents another one. One of the rules of combining orbitals tells us that when we combine 2 orbitals, we need to get 2 new orbitals. We say you can't create or destroy orbitals. So when I combine the s and one of the p's, I have to get 2 sp hybrids out. Okay. When an atom's trigonal planar, what we have to do is use what we call sp3 hybridization. sp2 hybridization. And when it's tetrahedral, we use what we call sp3 hybridization. So the whole point of hybridization is to make the arrangement of the orbitals match the electron pair geometry of the atom. 3 different hybridizations for 3 different electron pair geometries. Again, since everything we're doing has one of these 3 geometries, those are the only 3 we need. What questions do you have there? Okay. So if you want to assign hybridization to an atom, all you have to do is look at the electron pair geometry. So really you're counting number of electron domains. Is it 2, 3, or 4 electron domains? So I want you to copy down this molecule. And then we'll think about assigning hybridization to each atom. So one thing you're going to want to do when you look at a molecule and you're trying to assign hybridization, you need to imagine what's not showing. So what's not showing in a skeletal structure like this? All right, carbon atoms aren't showing, hydrogen atoms aren't showing, and there's one more thing that's there, but we don't draw it in. Lone pairs, yeah. So you might want to draw in your lone pairs explicitly. It'll help you assign hybridization. I'd like you to get to a point where you don't need to draw in the hydrogen atoms, but if it helps you, you can draw in the implied hydrogen atoms. So for instance, here there'd be one implied hydrogen, here there'd be one implied hydrogen, here there'd be one implied hydrogen. All right. So let's go through from left to right. I look at my nitrogen over here on the left. How many domains do I have on nitrogen? 2 domains. So what hybridization would that correspond to? sp. How about the carbon next door? Same, also 2 domains, so also sp. Go through, assign every atom in the structure. I'll do it as well. We'll reconvene in a minute. All right. Hopefully you've assigned the hybridization to each atom. One thing to note, hydrogen never gets hybridized. Hydrogen only has a 1s orbital. So it's kind of the one exception to all this. We never talk about hybridization for hydrogen. Another thing to note, the group that we started with, that CN group, does anyone remember what we call that functional group? That's right, it's a nitrile. But we often abbreviate it as just CN. So you've got to remember that when you see CN in a structure, that it looks like that, it's going to have a triple bond, and it's sp hybridized. A lot of people have made that mistake on the skill checker. All right. Any questions about any of the hybridizations we saw there? It does include oxygen, so this oxygen up here, I assigned sp3 because it's got 2 atoms that it's bonded to, and it's got 2 lone pairs. But I did forget to assign the hybridization of the other oxygen atom in the structure. So I should do that. It's bonded to 1 atom and has 2 lone pairs, so that would be what hybridization? sp2. All right, so if you can do that, you have done the most important part of Module 5. The second part is, okay, how do we now apply this to bonding? And, oh, sorry, I wanted to give a summary, and then we'll talk about how we apply it to bonding. So, when we're talking about hybridization, something's sp hybridized, it has two hybrid orbitals. We call them two sp hybrid orbitals. That means we use the s and two of the p orbitals to make them, or the s and one of the p orbitals to make them, and that leaves two unhybridized p orbitals. And if you think about how to draw them, hybrid orbitals always kind of look the same. Hybrid orbitals always have a big part and then a little part, so they always kind of point in one direction. We often ignore the little part. So that would be one sp hybrid orbital. The other sp hybrid orbital is going to point in the opposite direction. And then there would be two unhybridized p orbitals left over. One of them is going to go straight up and down, like this. I'm going to call this py. So we start with four orbitals, okay? We start with an s orbital, py, px. Well, maybe I'll put the labels below so they're more legible. Py, px, and then pz, which kind of goes into and out of the board. Those are the orbitals we start with. What we've done when we have sp hybridization is we've combined the s orbital with the px orbital. We've made these two new sp hybrid orbitals. The py orbital is left over, and the pz orbital is left over. Now, the pz orbital is going to be really hard for me to draw. I'll do my best, but it would go into and out of the page. I'm going to show you a model of this in a minute so you have some better picture of it. But the pz orbital would kind of go into and out of the page. So it's really hard to draw. So I've built the model. I will show the model, and then I'll pass it around so you can see what it looks like. Okay, so here's my little model of my sp hybridized atom. I've got my sp orbitals, which point across from each other. And then I've got my p, well, in this case, I'm holding it so that the pz is pointed up and down. And hopefully you can see that. And then the py is going towards you and away from you. If I turn the model like this, you can see that other p orbital. So we've got our sp hybrids, and then we've got our 2 leftover p orbitals. I'm going to pass that around. All right, so that's sp hybridization. Then the next possibility is sp2 hybridization. In sp2 hybridization, we're taking the s and 2 of the p's. We're making 3 sp2 hybrid orbitals. And we leave we leave 1 unhybridized p orbital behind. In each case, there's going to be a total of 4 orbitals. So, in this case, my hybrid orbitals would point in a triangle. So there's 1 sp2. Here's my second sp2. And here's my third sp2. They point in a triangle, and I would still have the pz orbital left over going into and out of the page. That's going to be hard to draw. I've got a model of this as well. All right, so here's my model of an sp2 hybridized atom. I've got the p orbital that's in green, and then my 3 sp2 hybrid orbitals. So if I hold it like this, you can see I've got the 3 sp2 hybrid orbitals pointed in a triangle, and then the p orbital coming towards you and going away from you. I'll pass that one around as well. So I'm passing it around. Okay. I can do it individually too, with anyone who wants.